What were the what's the highlights that you talked about here today? What did you find most useful and interesting?
We we did talk about the problem of assigning homework, and some of us think that it's possible to give assignments that that students can't fake, that really are indicators of learning, so that there are ways around that problem. I think most of us felt there were. Many of us are using flow solvers. Many people are using flow solvers. I haven't tried it myself with students, but because we don't have a site license, but some people are. Who would like to chime in on that? Who's actually using it?
Doug?
Well, I mean, we use Fluent in our second fluids class for mechanical engineers, not so much as a tool to teach fluid phenomena, but more as a service to the students who, if they're going to go out and practice, are going to have to use some sort of computational code, and to give them exposure to that. Opening it up, turning it on, solving something.
Okay, thanks. All right. Table number 2.
Yep.
This is so stressful.
Yeah, so the brave ones stayed.
Okay,
Yeah.
Let's hear from the brave ones.
Yeah, and our discussion was mainly around textbooks and CFD codes, and whether it's how we incorporate CFD and how we want to incorporate CFD in the courses.
So do you have any specific examples?
No, we didn't have examples. It was that part of the discussion was very sort of general.
Okay.
But we did talk a bit on how to put in the smartphone and iPad possibilities with these interactive softwares in classroom and in labs, because you can do something to make them find out things on flows around a cylinder or airfoil, for example, and then have them discuss that. And you can do that with an iPhone in 4 minutes. If you have to bring them to a wind tunnel, it takes longer time.
That's true.
The other discussion was about the textbook, how to make the textbook relevant, and the two things that came up was to have an equation sheet so that they have to write an equation sheet themselves for the exam. And the second one was to us to use peer instruction, where we enforce reading before class, asking the students to deliver something at the beginning of the class or 2 hours before via email or on a sheet of paper on the desk, where they have to summarize what they have read, and maybe also asking some questions about the text. And then the lecture is used to discuss the question they have after reading the text, rather than presenting the material that's in the text. So I think that's the tip from this table, to force them to read the book before class.
All right. Okay.
That's it.
Okay. Cool. All right.
I'm going to talk.
All right, Mark.
Okay, so we talked about a variety of things. First was kind of about homework assignments and the textbook. We felt like assigning a large reading assignment for the students is kind of overwhelming and usually not done by most students. Some suggestions were to assign a small reading section, so a section of a chapter, and focus like a quiz or concept questions on that section afterwards, and then kind of omitting that from in detail in your actual lecture, so they kind of have an experience of learning something on their own. Or to just not assign readings and just kind of assign references to the book, say this is in this chapter, and look it up on your own if you're interested. We talked about the idea of providing answers to questions, not the full solution, just the final answer. And what we came to a conclusion was that students tend to either work towards that answer and just think about how they can make their numbers work out to get that number, or even start the problem, get lost, and work backwards. And then you have these two converging solutions and doing some black magic and making it work.
I've seen that a lot this semester, actually.
So we've kind of agreed that we shouldn't provide any solutions.
In advance, you mean?
Exactly.
Okay.
In advance. We do feel it's important to grade homeworks to provide feedback to students, even if some of them are just copying solutions. Okay, then we talked about CFD, which the quick little like iPhone apps, they're kind of really interesting for instruction. Like if you want to talk about how lift and drag work, they can be useful, and just have students play with it for a little bit. We did feel like it's important for students to get exposed to building something from scratch. So even if they're building something that's simpler, something that uses like potential flow theory, that they actually like code the whole thing and it works and they're excited about it. That can be fulfilling to the students rather than just using this black box in a lot of occasions. So, did I miss anything?
Great job.
Okay. All right. Thanks. Okay. Karen.
All right, our group talked a little bit at the beginning about how to present theory to students and how we keep theory relevant to the students. And we thought that the best idea to present theory was to start with kind of a complex real-world example that they needed to want to solve, that they understand, they're in tune to, and then take that example and break it down into an element of that, of a simple model of that. So some aspect of that complex thing, you have a simple model, and that model should be a simple demonstration. Maybe it could be, a simple app or something that shows that, but somehow have a simplified model. And in that model, it's very important that you define all the variables that are important to that model that you're going to use later, and that you have the students try to make some observations or predictions about what's going to happen. So get them a little invested in what's going to happen in your demonstration. And then at that point, then you go to the theory. So they've at least seen something that they can relate to, something that they become at least a little invested in. And in that process, you've talked about the important parameters and the variables, and they've kind of come up with a predictive process. And we admitted that when we did this, it was very effective and that we should try to do it more often. The other thing is related to computational fluid dynamics is that we think it can be used very effectively also if you've already kind of taught Navier-Stokes, to kind of teach them how to do that it should be taught after or with Navier-Stokes equations. But it's important that they do a hand solution, a simple analytical solution by hand first, and then use the tool to solve that same simple solution to prove that it works, and then go to something more complex, something that they couldn't solve by hand, and so they can see the extension of this.
Okay. Thanks.
I'd like to bring up one other thing. So there's one other thing that I think came up in our discussion that was important, is that there's it's kind of this whole business of solving equations and getting predictions
Thanks, Jim.
I mean, if you think about it, when you started, it's kind of surprising that you can solve equations and get answers that actually match the real world. So there's a sense of wonderment there. We need to work on passing that sense of wonderment on to the students so that they also see that it's kind of exciting to be able to solve, quantitative equations and get answers that really do reflect reality. Yeah.
All right. Thanks. Yes.
Right. So in our table, we had quite a lot of discussion pretty much on all the 4 questions, but we started with CFD, and Jean was also part of our group here, and we talked about how to bring CFD into the classroom. Now, one of the examples is oftentimes we teach fluids with lab experiments. So one example would be to look for a good CFD package that's easy to spin up. One example is COMSOL, for example. I'm not making any market pitch for COMSOL. It just happens to have meshing everything in one go. You do a flow around a cylinder, for example, in the lab. These guys measure the pressure distribution. You can easily do the flow around CFD, and the match is pretty good here. And so they're like, wow, But to do this effectively, you can make use of your graduate students, if you're talking of an undergraduate class, and help them to do a video of a good introductory class on CFD, like just give the basics to demystify that this is not a magic box or black box, right? So that's one way of doing this. Then we talked about how do we reinforce concepts. So this came down to, do we have a good database of concepts questions? So because you could make use of this in pop-up quizzes, you could use clickers and so on. So right now, like some of us, we write our own concept questions, but the idea was maybe there should be a good pool of concept questions, not just exam questions alone. Then the other thing we talked about is using videos in the classroom. So more and more, of course, there's the MIT classic videos, but they're long, but you could always bring snapshots of those into the classroom. Like if you teach pipe flow, you can use transitions from laminar to turbulence and so on, with Rob Stewart talking with his pipe on and so on. But other times you could bring small videos, like Munson and Young, for example, and et al. There's 4 authors now. They have a whole database online as part of their textbook. So you could show small videos that have been done in research labs across the country, including Stanford, CDR, CSU, Minnesota, and all these places. So you could use those in the classroom as well. Then we ended up thinking about solution manuals. What do we do about this? So we said, can't stop anybody who wants to really copy from copying, but what you can do is at least vary the question selection. You can bring it from different textbooks, and you can sort of try and avoid that a little bit. But it's not entirely a solvable problem. So I think that's pretty much what we covered.
Okay.
Thank you.
All right. Any other comments?
One thing I would say is we shouldn't forget the multimedia fluid mechanics CD, which is very useful, and I think one of the nicest areas that I particularly enjoy is the part on surface tension phenomena, which is very visual, lots of videos, and easier to teach about, even to introductory physics students, than the rest of the material in there. Very closely related to physics, so I think it's excellent.
Okay. All right. Thanks, everybody.
Thank you.
Thanks for coming. And let's all give ourselves a hand.